Hi, pre-calculus honors. So today we're going to do notes on 3.6 and the theme is time is money. Our objective is to be able to use exponential equations to solve finance applications related to compound interest and annuities. So the saying goes, time is money. When we borrow money, we pay interest, and when we loan money, we receive interest. So the first thing we're going to do is we're going to talk about simple interest. So if I invest $500 at 7% interest for 10 years, and if it's simple interest, notice that 7% of 500 is 35. Okay, so since 7% of 500 is $35, at the end of the first year, you'll have your initial $500 plus $35 in interest. So simple interest, you're earning $35 a year for 10 years. So you would have $500 plus 35 times 10. So you would have $850 at the end of the 10-year period. So here's the formula for simple interest. A $500 initial investment. Our interest rate is 7% for 10 years. So congratulations. You earned $35 in interest at the end of the first year. Suppose the interest earned for year 2 was calculated using 535. So notice with simple interest, they used $500, your initial investment, every year to calculate your interest. But suppose that they used on year 2, $535. Notice that you would have $572.45 instead of $570 at the end of year 2. So why don't we think about time in years and amount in the account. So at the end of the first year, you had $535. Now, what if we calculated the interest in this way? So now we're using the 535 and we're going to multiply by 1.07. So you have, notice, $572.45. Then for year 3, we use the $572.45 and then calculate your interest. So you get to keep the 572.45, but you get 7% of that for interest. So this pattern, notice we would have 500 times 1.07 to the end. So notice this is the constant percentage growth pattern. So the value of an investment is an exponential function of time. Interest calculated using this method is called compound interest because the interest becomes part of the investment. Interest is earned on the interest. So simple interest, we're not going to talk about that ever again. We are going to talk about interest compounded annually. So go ahead and pause the video and take a look at the formulas in the blue boxes. Okay, let's do some examples. So for compound interest, here is our formula. And we are for part A, we're going to invest $500 at 7% interest for 10 years with interest compounded annually. That means once per year. So go ahead and pause the video and set up the equation for 1A. All right, so we had $500 as our initial investment, 7% interest, and our, notice we compounded once, so K was one time annually, and we ended up with $983.58, which is certainly better than the $850 from the simple interest. For this same investment set, simple interest was only $850. Go ahead and try part B, pause the video and write the equation and use your calculator to find out how much money you would have after 10 years if interest is compounded monthly. All right, so this time the K was 12 because you're compounding monthly. And again, I think this formula makes a lot of sense because, with the bank, their deal was you're going to get your interest compounded monthly. So I think this little part makes a lot of sense that they're not going to give you 7%. It's 7% APR, annual percentage rate. So you would make sense that at every month you would get a 12th of the 7%. So notice we have $1,004.83 at the end of the 10-year period, which is more than $983.58. So again, monthly, they are compounding your interest more often. Why don't you go ahead and try part C? But before we do that, maybe we should practice on the calculator for a second. There are a lot of ways you could use your calculator. You might want to start with the 0.07 divided by 12. So 0.07 divided by 12, hit enter, add the 1. Hit enter again. Now we are going to take that to the 120th power. And hit enter again and multiply by 500. So you could just type everything in, but it's kind of a parenthesis nightmare, so I like to do it in pieces like this. All right, why don't you go ahead and pause the video and try part C. Okay, so for part C, we had $500, and this time the interest was compounded quarterly. So it makes sense that we would have, there we go, 0.07 divided by 4 right here, because again, there are 4 quarters in the year. And notice we ended up with a little bit less than if our interest was compounded monthly, because you are compounding your interest only 4 times per year instead of 12 times per year. So go ahead and pause the video and try part D. Okay, so notice part D, $1,000.06 or $1,006.81. That would be more than compounded monthly, because now we're compounding our interest daily. So 365 times a year is more than 12 times a year. So we should end up with more at the end of that 10-year period. So lastly, we're going to talk about part E. Now, compounded continuously, that's kind of an abstract thought. It's not like I could, set a stopwatch, but bankers use the formula A equals P E to the RT. So there's E again coming up in so many interesting places. So we're going to use this formula to demonstrate how you would compound your interest continuously. So it would be more than daily. And we're going to go ahead and use 500. So again, more often than daily would be continuously per year. 500 and then E to the 0.07 times 10. So go ahead and grab your calculator, pause the video for a minute, grab your calculator, and find out how much money you'd have at the end of the 10-year period if your interest was compounded continuously. Okay, so we have $1,006.88. So a little bit better than if we compounded the interest daily. $1,006.88. All right, so what we're going to do next, we're going to do some more examples. We have, notice on all of these examples, we solved for the amount, but I might ask you to solve instead for an interest rate or a time. So what I would like you to do is pause the video and consider part 3, how you would write an equation to describe the situation. So for part 3, we have a $1,000 investment, and it's going to eventually grow to $10,000 with interest compounded weekly. That's 52 times a year at 5% APR. So notice we can use this equation. You could graph this, or you could solve it algebraically. If you wanted to solve it algebraically, you would divide both sides of the equation by 1,000 first. Now, if you, on your calculator, if you do 0.05 divided by 52 and add 1, you're going to get something, it's like 1.009615538. I would store that value. Or if we go ahead and just keep scrolling like we did for the last problem when I used the calculator, then you wouldn't need to store it. So you could do log of that 1.009615538. There you go. Of 10 equals 52 times t. So why don't we go ahead and use the calculator, and we can practice typing this into our calculator. All right, so the first thing you probably want to do, you probably start on the inside and do 0.05 divided by 52 and hit enter. Add 1 to that and hit enter again. Now notice we're going to do log of 10 divided by log of that number, because we're going to use the change in base property. So log we'll do log 10, make sure you finish up your parenthesis, divided by log of answer, or you could have stored that value if you wanted to. But notice if you hit second negative sign, that's answer. Okay, so that's the left side, and now we could divide by 52 to find t. And you get 46.07 years. Next question, it says, what interest rate compounded daily will double your money in 5 years? Go ahead and pause the video and write an equation that would describe this situation. I noticed in the previous example, I started with 1,000 and ended with 10,000, and I did get the t by itself. I had just divided anyway. So I think I'm going to start with $1 and end with $2. So we have to solve this equation for r. So we're going to have to take both sides of the equation to the 1 over 365 divided times 5 power. So go ahead and pause the video. I will tell you that the interest rate is 13.8 0.1387%. So you should get 0.1387. So go ahead and practice with the calculator and see if you can get 0.1387. So we do 2 to the 1 divided by 365 times 5 power and hit enter. There we go. All right, so we have 1 and some change there, and that is equal to 1 plus r over 365. So you can subtract 1. And now we have a small number, 3.79. It's at approximately times 10 to the negative 4. And we're going to multiply by 365 to find r. So r is 0.1387. So 13.87%. Okay, questions there? We're going to practice more with calculator in a separate activity. So in all of the investments that we've considered so far, the investor has made a single lump sum deposit. So suppose an investor makes equal regular deposits monthly, quarterly, or possibly yearly. This is an annuity situation. An annuity is a sequence of equal periodic payments. The net amount returned from the annuity is its future value. So we're going to talk about this formula right here. So go ahead and pause the video and read the blue box to see what each individual letter in the formula, what it would represent. So N is K times T, because it's equal periodic payments of R dollars of interest rate of I. So I is R over K, since R is the interest rate per compound period. Okay, so we also have a present value formula there. We're going to wait on that one. So let's start off with number 5. It says Amy contributes $50 per month into the a bond fund that earns 7.26% annual interest. What is the value of Amy's investment after 25 years? So we are actually saving money. And when we learn about present value later, this formula is actually used for a loan. And that future value we'll use for a savings annuity. So what we're going to do is we are going to, or some type of savings account. So what we're going to do is pause the video right now and see if you can use the formula for future value and write an equation, put all of these numbers in and see if you can figure out where all of the numbers go in the formula. Pause the video and give it a try. All right, so the interest rate was 7.26% and it was compounded monthly. So the payment was $50 per month. So that's how I knew it was future value, because we're not just contributing a lump sum. She's going to contribute $50 per month for 25 years. Okay, so that's why this is a future value, an annuity. So now we need to practice using the calculator. So let's just go ahead and grab your calculator. And again, you could do this many different ways. Go ahead and pause the video and we'll give it a try. Here's just one way you might want to do this. You might want to go ahead and do 0.0726 divided by 12 and store that under something. I don't know, how about X? There you go. So we're going to take X and we're going to add 1. So we're starting right here. Okay, I hit enter. And now we're going to take that to the 12 times 25 power. And I hit enter. We're going to subtract 1 and hit enter again. And we're going to divide by that stored value 0.0726 divided by 12. If we multiply this by 50, we end up with our future value, which is $42,211.46. All right, let's try the next problem. Linda contributes to the Celebrity Retirement Fund that earns 12.4% annual interest. What should her monthly payments be if she wants to accumulate $250,000 in 20 years? So notice for this one that she wants to do a monthly payment, an equal periodic payment, and it's a savings. So that's a future value. She's saving money and she's contributing a certain amount each month. So it's not a lump sum. We're not using the compound interest. We're going to use the future value. So go ahead and pause the video and see if you can write an equation to describe this situation. All right, check that you set it up correctly. And we're going to use our calculator now. So I like to start on the inside over here. So I'm going to go ahead and type in 0.124 divided by 12. I will store that. Under X is fine. So I'm going to start on the inside. So 0.124 divided by 12. If I add 1 to that and hit enter, and now I take it to the 12 times 20 power and hit enter again. Subtract 1. Now I divide that by my stored value, 0.124 divided by 12, which was X. And now, since I'm going to have to multiply that by R to get $250,000, right, I would have to take $250,000 divided by this value to get R. So answer is a second negative sign. So I put 239.41. So that would be my equal periodic monthly payment of $239.41. Okay, so an annuity is a sequence of equal periodic payments. The net amount put into an annuity is its present value. The periodic and equal payments on a loan or mortgage constitute an annuity. So we're going to use the present value formula for a loan. So go ahead and read number 7. And we have the formula up here, or it might help that I also summarized all the formulas here because, again, N is K times T and I is R over K. So go ahead and fit everything into the equation, pause the video, give it a try. So I know I'm not just using my compound interest formula because, again, we have a equal periodic payment. We're paying monthly to pay off this loan. So $4,500 is my present value because the bank is handing me $4,500 today. So that's my present value, and I need to have equal periodic payments over a period of 3 years to pay back the loan. So we are going to solve for R. So go ahead and pause the video and type this into your calculator and see if you can get the equal periodic payment. All right, so you're paying $145.73 every month to pay back that $4,500 loan over a period of 3 years. So notice the present value formula is a little bit different because, again, present value we're using for a loan. Now, hopefully the calculator is getting a little bit better, but we need more practice. Let's do one more example. This last one is called, what did you really pay for that house? So this is a loan, so we're using the present value formula. So go ahead and pause the video and use that formula, fit everything in. And we're going to figure out what your payment was if you had a 30-year loan at 6% APR and you borrowed $200,000. So we still might be having trouble with the calculator, but for now, let's just make sure that we can set it up correctly. And if we need more practice with the calculator, we will practice that another time. So notice we use the present value formula. Our present value is $200,000. The bank is handing that to us today. We have equal periodic payments of capital R. That is not the interest rate, that is the payment. Notice it was 0.06 is the interest rate, and we're going to compound the interest monthly for 30 years. So when you solve for R, hopefully you have approximately $1,200. So what we're going to do now is figure out how much did you really write a check for? What did you actually take out of your pocket and hand to the bank? So go ahead and grab your calculator. $1,199.10 monthly for 30 years. So you really paid $431,676. So $431,676 on a $200,000 loan, that sure seems like a lot of money, right, that you have to pay back. But again, you are paying interest on that loan. You are holding on to their money for 30 years. So we're going to do the same thing, but this time we're going to see what happens if you have a 15-year loan instead of a 30-year loan. So go ahead and pause the video and fit everything into the equation and solve for R. So let's make sure you put everything in correctly. We have $200,000 as our present value. We're going to try and pay it back over a period of 15 years at 6% APR with an equal periodic payment of R. If we solve for R, we get $1,687.71. So notice our monthly payment is more than with a 30-year loan. However, watch what happens. I'm going to multiply this by 12, so you pay this monthly for 15 years. So again, your monthly payment was higher, but you pay $303,787.80 back on a $200,000 loan. So there you go. So notice we are actually paying less interest if you go ahead and have a 15-year mortgage instead of a 30-year mortgage. So nice job, everybody.